Something happened underneath the French-Swiss border this year that kept some of the world's most brilliant physicists awake at night. Not because the result was unexpected, because it was impossible. 50 years of the most rigorously tested scientific theory in human history says it cannot happen. And yet the data is sitting there, confirmed by two completely independent experiments, pointing at something that exists just beyond the edge of every equation we currently possess, something we cannot yet name. Something that may force us to rewrite the entire story of what matter, energy, and reality itself actually are. If you have ever wondered whether there is more to the universe than what our best science can currently describe, this is the moment that question stopped being philosophical and became measurable. There is a machine running beneath Europe right now. It is called the Large Hadron Collider, a ring 27 kilometers in circumference buried under farms and villages, where beams of protons are accelerated to within a hair's breadth of the speed of light and then slammed together head-on at energies that have not existed anywhere in our universe since the first fraction of a second after the Big Bang. I have spent a significant portion of my career building theoretical frameworks for what particles like these might do at extreme energies. And I want to be completely honest with you. When I sat down with the results that came out of CERN this year, I held them for a long time before I felt ready to discuss them publicly. By the end of this, I'm going to show you three specific things. First, exactly what was detected and precisely why it does not fit. Second, why two entirely separate experiments, built by different teams using different instruments, are independently pointing toward the same answer. And third, what it actually means if they are right. Not just for physics as a discipline, but for every assumption you have ever held about the nature of reality, about what matter truly is, about what the universe is constructed from underneath everything you can see and touch. Because if CERN's data continues to hold, and right now all the evidence says it is holding, then the foundational theory that has explained every particle experiment for the last 5 decades has developed a crack. And whatever's hiding inside that crack is something no living person has ever encountered before. Let me set the scene properly, because understanding the scale of this moment requires understanding what we are actually dealing with. Wherever you are sitting right now, everything surrounding you, the surface beneath you, the screen in your hands, the air moving through your lungs, is constructed from atoms. Atoms are built from something smaller, protons, neutrons, and electrons orbiting a nucleus. For a long time, we believed that was roughly the deepest level of the structure of matter. It is not. Protons themselves are assembled from something smaller still, particles called quarks, 6 varieties carrying names that suggest whoever invented them was running on too much caffeine. Up, down, charm, strange, top, and bottom. These quarks are bound together by a fundamental force called the strong force, carried by particles called gluons. The entire elegant architecture is described by a framework called the Standard Model of Particle Physics. That theory, assembled across decades by hundreds of researchers and tested across thousands of experiments, is arguably the most successful scientific framework in the history of human civilization. It predicted the existence of particles before we ever detected them. It correctly described the behavior of matter at scales so tiny that the number of zeros involved strains comprehension. It is a genuine masterwork of human intellectual achievement, and it is almost certainly incomplete. We have known for years it cannot be the whole picture. It fails to account for gravity, it cannot explain dark matter, which comprises roughly 25% of the universe and which has never been directly detected. It offers no explanation for why matter outnumbers antimatter, which means it cannot fully explain why anything exists at all. The crack has always been there. In 2026, for the first time in a very long time, we have a precise, measurable, hard-to-dismiss location where that crack is visible. Here's exactly what they found. Inside the LHC, when protons collide at colossal energies, the collision briefly generates exotic particles that do not exist in ordinary matter, particles that survive for unimaginably short durations before transforming into something else. One of those particles is called a B meson. A B meson is a particle composed of a bottom quark, also known as a beauty quark, bound to a lighter quark. It exists for approximately 1 picosecond, meaning 1/1,000,000th of a second, and then it decays, transforming into other particles entirely. The standard model makes extremely specific and precise predictions about how a B meson should decay, which particles it should produce, at what angles those particles should emerge, and how frequently each possible decay pathway should occur. These predictions have been tested before. They have generally held up, until now. The detector responsible for this result is called the LHCb experiment, the Large Hadron Collider Beauty Experiment, a detector the size of a 5-story building designed specifically to capture and study these kinds of particles. What this team investigated was an extraordinarily rare variant of B meson decay called an electroweak penguin decay. The name derives from the shape of the Feynman diagram drawn when calculating it. If you tilt your head and squint, the lines on the diagram bear a passing resemblance to a penguin. Physicists named it in a pub. The physics is what matters. In this particular decay, a beauty quark transforms into a strange quark, and in the process, the B meson produces four particles: a kaon, a pion, and two muons. The standard model predicts this should occur only approximately once in every million B meson decays. It is a vanishingly rare event. The research team watched 650 billion B meson decays to accumulate enough examples to measure properly. 650 billion. They sifted through data collected between 2011 and 2018, searching for this one in a million occurrence. They found it. And what they found does not match the prediction. When they measured the angles at which the decay products emerged, the precise geometric pattern of particles radiating outward from the decay point, those angles disagreed with the standard model's forecast. Not by a marginal amount, not by something that could reasonably be dismissed as measurement noise. The discrepancy sits at 4 standard deviations. In physics, the threshold for claiming a confirmed discovery is 5 sigma, corresponding to a 1 in 1. 7 to million probability that the result is a statistical fluke. 4 sigma represents a 1 in 32,000 chance. This is not a confirmed discovery yet, and I want to be straightforward with you about that distinction. But it is far too substantial to dismiss, and what makes this particular result genuinely unsettling to the physics community is that it did not appear in isolation. There is a second detector at the LHC called CMS, the Compact Muon Solenoid. It is a completely different instrument, constructed by a completely separate team, operating with completely different systematic errors and entirely different analytical methods. When the CMS team examined the same type of B meson decay, they found the same anomaly, the same deviation, the same disagreement with the standard model's prediction. Their result carries less statistical weight because their data set is smaller and their measurement less refined, but the direction of their discrepancy matches. When two independent experiments using different hardware, different personnel, and different analytical approaches arrive at the same unexpected answer, that pattern does not describe noise. That pattern describes a signal. I have spent enough time in this field to have watched promising anomalies evaporate when additional data arrived. That happens regularly, and the field is genuinely humbling in that way. But I have also learned to recognize the texture of something real. This has that texture. The standard model is not merely failing to predict the rate at which this decay occurs. It is failing to predict the geometry of the event, the spatial orientation of the particles as they scatter outward. That is a fundamentally harder discrepancy to explain away. A rate anomaly can sometimes be resolved by accounting for complex internal quantum corrections. An angular distribution anomaly, the way particles orient themselves relative to one another in three-dimensional space, points specifically toward the presence of something the model does not contain. Something new. Something that has been present all along, hovering just beyond the boundary of what our equations could resolve, making its influence felt in the geometry of a decay lasting 1/1,000,000th of a second. There are several theoretical candidates for what that something might be. One leading possibility is a hypothetical particle called the Z prime. Consider the Z boson, one of the carriers of the weak nuclear force, the force responsible for radioactive decay. The Z prime is a theorized heavier cousin of the Z boson, predicted by several extensions of the standard model, that would interact with quarks and leptons in subtly different ways from what current theory anticipates. If a Z prime exists, it could appear as what physicists call a virtual particle, existing only fleetingly, too briefly to ever be directly observed, but long enough to alter the outcome of the decay. Think of it as a presence that never shows up in any photograph but consistently rearranges the furniture. The angular distribution emerging from the B meson decay could be exactly the kind of rearrangement a Z prime would produce. A second candidate is something called a leptoquark, a particle that would bridge two families of matter that the standard model currently treats as entirely separate, quarks and leptons. If leptoquarks exist, they could mediate this decay in a way that generates precisely the kind of angular anomaly being measured. Both the Z prime and the leptoquark are legitimate, peer-reviewed, theoretically rigorous proposals. They are not fringe speculation. They appear regularly in the highest impact journals in the field. And the data published by CERN in 2026, submitted to physical review letters and already accepted for publication, has been described by particle physicist William Barter of the University of Edinburgh, a researcher working directly on LHCb, as among the most significant results from the LHC in several years. Physicists do not deploy language like that carelessly. Now step back from the detector entirely. Step away from the quarks and the mesons and the 4 sigma deviations. Think clearly about what we are actually saying when we say the standard model may be broken. Because the standard model does not only describe exotic particles generated inside an underground accelerator, it describes everything. Every chemical reaction currently occurring inside your body. Every photon reflecting off this screen and entering your eye. Every atom in every cell of every living organism on this planet. The standard model is the deepest description of physical reality that human civilization has ever constructed. When we identify a crack in it, we are not identifying a problem with a theory. We are identifying a gap in reality itself, a location where the universe is provably doing something that our most sophisticated tools cannot explain. What the LHC is observing when those angles disagree is not a particle misbehaving in controlled conditions. It is reality leaking through a seam we did not know existed. Whatever lies on the other side of that seam, whether it is a Z-prime, a leptoquark, or something that has not yet been named, it has been present throughout the entire history of the universe. It was there when you were born. It is threading through every atom in your body at this precise moment, invisible, intangible, and until this year completely undetected. The geometry of a 1 in a million decay, buried inside 650 billion recorded events, finally whispered its presence to a detector the size of a building beneath a mountain on the Franco-Swiss border. When I first genuinely sat with these numbers, not as material to be communicated, but as mathematics whose weight I could feel directly, my initial reaction was not excitement, it was vertigo. Because I know what the standard model is. I understand how difficult it was to construct. I know how many exceptional people across how many decades dedicated their working lives to confirming it, reinforcing it, and defending it against alternatives that turned out to be incorrect. And I know that what the LHC is showing us now is not a reason to discard it. The standard model is not broken, it is bounded. It resembles a map of extraordinary accuracy for everything within its borders, but those borders are not the edge of the territory. There is more. And what I keep returning to, after setting the papers aside, is this. If something exists that the standard model cannot account for, then our understanding of what matter fundamentally is contains a hole. And a hole in our understanding of matter is a hole in our understanding of everything without exception. The surface you are sitting on right now, the air currently filling your lungs, the neurons firing as you process these words. If there are forces or particles threading through all of that which physics cannot yet perceive, then in a very concrete and literal sense, you do not know what you are made of. None of us do, not yet. Now let me fulfill every specific promise I made at the opening of this video, because I made precise commitments and I intend to honor each one. I told you I would show you exactly what was detected and why it fails to fit the existing framework. Here is the straightforward answer. Physicists at CERN measured the geometric shape of a rare particle decay, the electroweak penguin decay of a B meson, and found that the angles at which the decay products emerge disagree with the standard model's predictions at 4 standard deviations, a discrepancy carrying only a 1 in 32,000 probability of being random noise. The standard model contains no mechanism to produce that geometric shape. Every correction calculable within the theory, including the complex internal quantum processes theorists have attempted to use in accounting for the anomaly, falls measurably short. The data, published in Physical Review Letters in 2026, is unambiguous in this regard. I told you I would explain why 2 independent experiments are converging on the same answer. Here it is. The LHCb and CMS detectors at CERN, assembled by separate teams using distinct technologies and operating under different sources of systematic error, both analyzed this decay and both measured deviations in the same direction. That cross-experiment agreement represents the most powerful form of evidence available in experimental physics. 2 entirely independent sets of measurements examining the same phenomenon, each finding something that should not be there according to the best theory we have. I told you I would show you what it means if they are right. Here is the honest answer. If this anomaly holds, and the researchers leading this work express confidence that the signal will only strengthen as new data is incorporated, since LHCb has already collected 3 times the volume of B meson data since 2018 that has not yet been fully analyzed, then the standard model requires extension. Something exists at the fundamental level of matter that our most complete theory does not contain. Something that has been invisibly present in every piece of matter in the universe since the beginning of time. And we are, right now, in 2026, for the first time beginning to measure its fingerprints directly. That is not a routine scientific update. That is one of the most consequential scientific moments in a generation. And it opens directly into something even stranger, because there is another question resting just beneath this one, a question that this discovery compels us to confront. If there are particles or forces that have gone undetected until now, particles that interact with matter in ways our equations cannot capture, how many of them are there? What else might be threading through you at this moment that physics currently cannot see? That question sits at the center of the next video in this series, where we examine what happens when particle physics collides directly with the mystery of dark matter, the 25% of the universe whose existence we confirm through its gravitational effects, but which has never once registered in any detector anywhere on Earth. There is a version of this story that circulates in press releases and science headlines in which discovery arrives cleanly. One day the answer is unknown, the next day it is established. The breakthrough appears like a thunderclap, sudden and undeniable. That is almost never how it actually unfolds. What actually happens looks more like this: a 4 sigma deviation in an angular distribution, buried within 650 billion decay events accumulated across 7 years. Two teams in different sections of the same facility independently growing, uneasy about the same number. A paper submitted quietly to physical review letters in late 2025, accepted in 2026, and received not with fanfare but with a kind of collective held breath, because everyone who genuinely understands what it contains knows what it might imply, and no one wants to say it too loudly before the data reaches full confirmation. This is what the actual edge of knowledge feels like from the inside, not triumphant, careful, tense, slightly afraid, not of being wrong, but of being right. Because being right means everything downstream of this result must be reconsidered. Theorists return to their notebooks. Experimentalists design new runs, new detectors, new analytical approaches. Graduate students commit the next decade of their careers to pursuing whatever this anomaly is pointing toward. The map gets redrawn, and maps being redrawn generates discomfort even for the people who always knew the old version was incomplete. What CERN is attempting beneath that mountain, what thousands of researchers across dozens of countries are collectively trying to accomplish, is among the most purely human endeavors I can conceive. They are trying to observe something smaller than anything the eye can resolve, faster than anything the conscious mind can track, operating at energy scales that have not existed since the universe was a fraction of a second old. And they are pursuing this not because a commercial application is waiting, not because any government required it, but because somewhere deep in the structure of human curiosity there is an unrelenting compulsion to understand what things are made of, to keep pulling the thread, to keep asking what lies underneath. That compulsion is as ancient as science itself, and right now in 2026, the thread is pulling back. Here is what occupies my thinking when I sit with this result at length. The particles inside the LHC that are producing decay patterns the standard model cannot predict are not exotic or unusual in any cosmic sense. Mesons form in high-energy collisions, and high-energy collisions occur constantly, everywhere, in the cores of stars, in cosmic ray showers raining down through the atmosphere directly above you at this moment, and throughout the early universe when everything was unimaginably dense and energetic, which means whatever new physics is shaping those decays has been shaping them everywhere across the entire history of the universe. It did not begin when engineers switched the LHC on. It was always operating. We simply lacked an instrument sensitive enough, a dataset large enough, and a measurement precise enough to detect its fingerprints until this year. Think about what that means in terms of duration. For the entire 14 billion year history of the universe, something has been threading through every particle interaction, quietly influencing outcomes in ways that deviate from what our most complete theory predicts, and we could not see it. The universe has been carrying a secret written into the geometry of its most fundamental processes, and the first time we have ever managed to read even a fragment of that secret required 650 billion individual measurements, 7 years of accumulated data, and 2 independent detector systems agreeing on what they saw. The fact that we could detect it at all, given those parameters, is itself remarkable. The fact that we did detect it suggests we are finally operating instruments capable of reading the universe at a resolution it previously kept hidden from us. There is something worth sitting with honestly in that recognition. Every era of physics that has extended beyond the previous boundary, every moment when the map was redrawn to include territory that was always there but previously invisible, has permanently altered the way human beings understand their own existence. Newtonian mechanics revealed that the same mathematics governing falling apples governs orbiting planets. Quantum mechanics revealed that at the smallest scales, certainty dissolves into probability. Relativity revealed that space and time are not fixed backdrops but dynamic participants in physical events. Each of these frameworks felt complete until the next layer became accessible, The standard model has felt complete for 50 years. The data from 2026 is suggesting, with a precision that serious physicists are treating seriously, that the next layer is becoming accessible right now. Whatever emerges from this anomaly will not invalidate everything that came before it. The standard model will remain extraordinarily accurate within its domain, exactly as Newtonian mechanics remains extraordinarily accurate within its domain, but the domain will expand. The territory beyond the current border will begin to be mapped. And the particles or forces discovered in that new territory will almost certainly change our understanding of what matter is, what forces act upon it, and what the universe is constructed from at its most fundamental level. You are made of that matter. Whatever is threading through it that we cannot yet see is threading through you. The discovery does not feel distant. It is personal in the most literal physical sense possible. If this shifted something in how you see the reality surrounding you, the next video in this series is already waiting, and it goes deeper still into the territory this anomaly is opening up. Subscribe so you do not miss where this investigation leads next. Drop a comment right now telling me which side of this you land on. Is this a statistical echo that more data will eventually absorb within the standard model, or is it the first confirmed fingerprint of something that will rewrite physics entirely? I read every comment and I will be in the discussion within hours. The universe is stranger than it appears. The evidence for that is now sitting in physical review letters. And the next question it forces us to ask is stranger still.